So we are going to go over example 4 again. So we left off, it's a little bit confusing. Okay, and now we've done it once. Let's go over it again in a little bit more organized fashion. And I got a picture this time. Accompany. All right, so example 4 said, find the line tangent to the right-hand hyperbola branch defined parametrically by x equals a secant of t and y equals a tangent of t, where t goes from negative pi over 2 to positive pi over 2, all right? So basically, when you define the derivative of something that's defined parametrically, look at this here, like x gives you a value that you got to computate, depending on what t is. And y, you actually got to computate as well, depending on what t is. First off, let me show you the graph, okay? This graph right here, this is the right-hand part of a hyperbola right here, okay? This line in blue. And we want to find the tangent right at where t equals pi over 4. That's right there. So we want to find this tangent line, okay? Well, if I want to find out coordinates on that graph, first of all, I have to know the t value. For example, if my t value is negative pi over 2, because that's a low height, what we said, right? Well, then my x is the secant of negative pi over 2, okay? And my y is the tangent of negative pi over 2, okay? So if I were to keep on going through, I'd say negative pi over 4, find the secant of it, and then the tangent of it. 0, find the secant of 0, tangent of 0, and so forth, all the way pi over 4, pi over 2, and they don't make you do that because they give you this point right here. That is the point where tan is pi over 4, meaning the secant of pi over 4 is your x value. The tangent of pi over 4 is your y value. So they're getting that to you. You don't have to figure that out, okay? I know this is a confusing question because we really haven't dealt with anything parametrically yet, but it kind of just works its way back to the same old thing. So if I want to find the equation of the line tangent, well, I'm still going to use our go-to equation of a line, y minus y1 equals m times x minus x1, where I need 3 things. I need an x and a y. Oh, look, I have an x. I have a y. The only thing I need is my slope. And in calculus, slope is the what? The derivative. Thank you very much. And how do we find the derivative of something parametrically? Well, we take the derivative of our y and put it all over the derivative of our x. This will also give us our slope. Once we have that, we just plug it in. And that's it. So all we need to do is really find the derivative there. Okay? So, my slope is going to equal the derivative of the y function on top, which is tan of t, all over the derivative of the x function, secant. And we simplify it. And that will end up being our slope. So let's go ahead and simplify that. Right? What is the derivative of tangent? Secant squared of t. Okay, what is the derivative of secant? Yeah, secant, and in this case it's t, but secant of t times tan of t. Right off the bat, I know I can cancel something. What can I cancel? Yeah, the secant. So one of these cancels with one of these. So now, I have secant of t over tan of t. I have secant of t. I can simplify these even further by converting them to their sine and cosine. Secant is what? 1 over cosine. And what's tangent? Sine over cosine. Now, I should write these t's. I get in the habit of not writing them until the end, but I should write them all the way through. And now I can cancel out what? Okay, this cancels with this. So I'm left with 1 over sine. What is 1 over sine? Yes. 1 over the sine of t is the cosecant of t. What point is this slope at? T is what? So all I'm going to do is I'm going to figure out what's the cosecant of pi over 4. Now, if you remember, pi over 4 is radians. That's actually 45 degrees. That's the same thing as saying the cosecant of 45 degrees. It's the same thing. All right? So, if I draw a 45, 45, 90 triangle, 45, 45. I mean, some people commit these denominators, but if you know the triangles, then you don't have to. 1, 1, radical 2. So I'm going to find the cosecant of this angle here. Well, this is opposite. This is adjacent. This is hypotenuse. All right? If sine is opposite over hypotenuse, that means cosecant would be what? It's the reciprocal, right? It's hypotenuse over opposite, which is the hypotenuse over opposite. Radical 2 over 1, which is radical 2. This is the derivative, which is also known as a slope, which also, for our purpose, is the m value. All right? This is our m value. So, after we did all that nice, fine work, our m value is radical 2 times x minus our x value, radical 2, and that equals y minus my y value, which is 1. You are just taking the derivative of two functions and putting them in a fraction when you find the derivative parametric. Okay? I hope it was a little bit more clear. This isn't something that's done a lot in calculus, so I don't expect to see it a ton, but it happens from time to time. Now it gets back to sanity. Now we're back to sanity. Okay? So the power chain rule. The power chain rule. All right? If I want to take the derivative of some function u raised to the power n, well, I do what I normally always do, which is this. Right? I bring the n, my exponent up front, multiply by it. I subtract my exponent by 1. But now, since it's chain rule, I multiply by the derivative of whatever inside my parentheses. And to be honest with you, we've always been doing this, you just haven't known it. I'll explain it to you in a second. So, forget about these notes for a second here. We'll come back to this. I just want to get this out of your mind. If I ask you what's the derivative of 3x squared, what is it? That is 6x. But really, you use the chain rule here. How come? I take my 2, bring it out front. 2 times 3 times x. I shrink my exponent by 1, right? Which gives me this. But then I multiply by the derivative of what's in the parentheses. What's the derivative of x? So you still get this. I mean, you've been doing it, you just haven't realized. So we're going to do the same thing, but now it's not just an x in here anymore. Now, my friends, there might be something like 3x squared plus 2 all cubed. Okay? So, let's go over that. And what was that over here? That's the FU function. You will see it like, I kid you not, you will see it like this in some books. d dx of the function u. The function with respect to u is f of u. Who? U. That's how you remember. You hear that? I take the derivative of the function f of u times u. So it's d f u. It's f u. Who? U. That's who it is. So don't ever forget, you always got to multiply by that u at the end. All right? So, here we go. Ready? Let's handle this just like we did. I can do u substitution here, but to me, they just, I don't know. I can do it both ways. I'll show you. Let's do the u substitution. I can say, I can do it first or second. I'll do the normal way first, I'll do the u substitution second. Okay. So this is going to be 3 times 3x squared plus 2, and I subtract 1 from the exponent, times the derivative of what's in here. What is that? 6x. What a coincidence. Alright? So now I just combine everything. Make it all nice and neat. 6x times 3 out front. And that's going to be 18x. Times 3x squared plus 2 squared. There you go. That's the derivative. That is f prime of x. Right there. Why is it what? Why did I put this 3 in front here? Because don't I have to take n and multiply it by whatever the coefficient is? So this 3, yeah, 3 comes out front, and multiply it by whatever the coefficient is. Technically there's a 1 here, isn't there? 3 times 1 is 3. I leave the parentheses the same, and then I subtract 1 from the exponent to make it 2. And then I multiply by whatever the derivative of the function inside the parentheses is. Normally it's always an x, so each 1. We don't even do that because we just know it's 1. But now, it isn't just an x anymore. So the derivative of the inside is 6x. So I need to multiply that into my coefficient. Alright? So that's just doing it, just kind of knowing that you always got to multiply by the derivative on the inside. Some people like to be a little bit organized, okay? They like to say, let u equal 3x squared plus 2. Okay? So now I've got u cubed. Because that's what you're cubing, isn't it? 3x squared plus 2. If I were to take the derivative of this normally, wouldn't it just be 3u squared? But now I need to multiply it also by the derivative of u times u prime. Well, if this is u right here, then u prime is what? What's the derivative of that? So now I'll just plug things in. Okay? I'll just plug things in. I have 3 times u, which is 3x squared plus 2 squared, right? So it's my 3 here, my 2 here. Times u prime, which is 6x. It's the same thing we end up with here, which means it leaves the same place there. Yeah, sure, you get 18x times 3x squared plus 2 squared. Same thing. Same thing. Now, why do people do this? Because sometimes, mind you, when they have this, and they take derivatives, they try and do it quickly and get, messed up. When you just have this, taking the derivative of this is easy. It's 3u squared. Anyone can do that. Even people who struggle with calculus. So they take it out, they do it, and they put all the more complicated stuff back in. Most of you, they just do it different ways. That was a mixed signal. Alright, anyways. Y prime would be, well, first of all, you should know that sine with a little 5 here in front of the x is the same as that. So I need to bring that out front, keep my parentheses the same, shrink the exponent by 1, and then multiply by the derivative of whatever's in your parentheses. And that is, what's the derivative of sine? Cosine of x. That is the derivative, which would mean that is also the slope. They want to know that value right at this point. So for any x, I'm going to put in pi over 3. So I've got 5 times the sine of pi over 3. Remember, that's still to the 4th. Times the cosine of pi over 3. Now, because we have a fear of radians, pi is the same thing as 180. Right? It is. Very good. Pi over 3. This is like 180 pi, right? So 180 divided by 3 is 60. So technically, if you wanted to look at it this way, these are 60 degrees. Okay? That's going to help us do this a little bit easier. Because I know my 30, 60, 90 triangle. This is 30, and this is 60, and this is 90. 1 is not, it looks like a 45, 45. But, what can I say? Radical 3 and 2. All right, well, here's 60 degrees. This is the hypotenuse. This is opposite. This is adjacent. All right? So sine is opposite over hypotenuse, which would be radical 3 over 2. This is the value of the sine of pi over 3. So it's 5 times radical 3 over 2 to the 4th power. Times. Now cosine is adjacent over hypotenuse, which is 1 over 2. So that takes this whole place, so times 1 half. Now, I can do this in my head, and you guys should be able to too. How come? Well, we have 5 times, and we still have our 1 half here, times. I'm going to do these to the 4th power. Okay? Let's go off to the side here. Radical 3 to the 4th over 2 to the 4th. Well, 2 to the 4th is what? 2 times 2 times 2 times 2 is 16. What is radical 3 to the 4th? Well, that's radical 3 times radical 3, which is 3, isn't it? Times radical 3 times radical 3. Yeah, because think about it. 3 times 3 times 3 times 3 is 81, which is still 9. So guess what? Let's multiply the tops and the bottoms. So I get, this is stacking over 1, 45 over 32. Does that reduce anything? Nope, 5 and 9, no. That's right. That's the slope. Because the cosine of 60 is 1 half. Right here. The cosine of 60 is 1 half. Okay? All right, the last one, example 7. Show that the slope of every line tangent to the curve, y equals 1 over the quantity 1 minus 2x cubed, is positive. Okay, it's positive. I'm going to show you guys something that will probably help you guys out a little bit here. All right? Yes, it will. Now, when it says slope, we know that means derivative, right? So let's take the derivative of this. What are you guys thinking when you see that? Derivative is what? You know what it is? Like, how do I do that? Wait, no, the whole thing.
Whole fraction?
Yeah.
Quotient.
Yeah, the low d high minus high d low drawn, square below. I'm going to make this easier for you. I'm going to make this easier right now. Isn't this the same thing as saying 1 minus 2x to the negative 3? Because if that was like that, wouldn't I flip it, numerator, denominator? If it was like this, wouldn't I have to flip this down here to make this exponent positive? Which is what I did here. So let's put this back in the numerator. If you can recognize to bring things in the denominator up to the numerator, and you don't have to use that quotient rule, that might be a little bit easier for some of you guys. Meaning, I want to bring this back up here, which means I got to negate the exponent. Does everybody follow what I'm saying? Okay. Now, let's use a power rule here. What do? I bring the negative 3 out front, don't I? Negative 3 out front. And then I do what next? I subtract subtract 1 from here, and then I multiply it times the derivative of the inside parentheses. What's the derivative of the inside here? Negative 2? Yeah. Sine 6. So let's clean this up. I have negative 3 times 1 minus 2x to the negative 4 times negative 2. So how can I prove that this is always positive? And by the way, this is the derivative right here. How can I prove that it's always positive? Well, let's clean it up a little, okay? Let's multiply our negative 2 times our negative 3. So now we got 6 times 1 minus 2x to the negative 4. All right? Now, let's simplify that even further. To simplify that, I got to make the negative exponent positive, don't I? Which means I'm going to take that expression and bring it down, right? And then that will make that exponent positive. So now I have 6 all over 1 minus 2x to the 4th. Okay, that's as simple as it can be. How is that always positive? Well, the top is always positive, right? So for a fraction to be positive, both the top and bottom should be positive. Or they're supposed to be negative. This top will never be negative. So the top is always positive. The numerator is always positive. So in a fraction, a positive or a positive gives you a positive. So how can I say the denominator is always positive? How come? Take a look at it. What about the exponent? No, it is. If you square something, whether it's a positive or negative, what's the answer? It's always positive because it's a negative. It's a negative. That works for any even exponent, doesn't it? Because it always compares with 2, isn't it? So the denominator is always positive. How come? Because the even exponent will never give you a negative answer. Will never give you a negative answer. Even exponent is never negative. So a positive always a positive will always be a positive.